A very good day to Dr. Siti Saleha and fellow students. We are from Group 3 and we will give our presentation about our group assignment. First of all, let me introduce myself and my group members. My name is Kong Wen Yu, the leader of Group 3, and my group members are Mashira Laila, Oyifong, Muhammad Ubadullah, and Nayo Hakimi. For the task 1 is the wind bridge oscillation. So now I will pass my time to Nayo Hakimi for the presentation of the theory.
Assalamualaikum and hi, my name is Nael Hakimi. Now I will continue the theory of Windbridge oscillator. Windbridge oscillator consists of 4 resistors and 2 capacitors that look like a bridge. It's a two-stage RC coupled amplifier circuit. Two-stage RC coupled amplifier is an excellent resonant frequency, low distortion, and easy to tune its output frequency. The maximum frequency is up to 1 MHz and the phase shift angle is 0 degree. It's follow Barkasian criteria, which state the condition for the oscillation to occur and sustain are A multiplied with beta is equal to 1 and the phase angle of the loop gain A and beta must equal to 0 at the oscillation frequency. Windbridge oscillator can be divided into two parts, which are amplifier and feedback network. For amplifier, it consists of two resistors where we can calculate the gain A. The A must equal or greater than 3 in order to start the oscillation and get the sustained frequency. The feedback network part is a combination of series and parallel of resistor and capacitor, which be the input for the amplifier. The gain for the feedback network is beta. Beta must be equal to 1/3 for oscillation occur. We also use the feedback network part to determine the frequency of the oscillation. Next, I will pass back to Wang.
So for now, I will present about the evidence and stimulation. For the oscillation frequency, it can be calculated manually. The equation of the oscillation frequency F equals to 1 over 2 pi RC, where R equals to the resistance of the resistor and C equals to the capacitance of the capacitor. Throughout the calculation, we can get to know the frequency equals to 482.29 Hz. For the calculation of gain, the formula is A equals to 1 plus R2 over R1. By adjusting the value of R2 from 1 kilo ohm to 10 kilo ohm, we can obtain 10 different values of gain. So this is the Windbridge circuit, and this circuit has been stimulated using Multisim Live software. The circuit has been stimulated by using 3 different values of R2, which are 1 kilo ohm, 2 kilo ohm, and 3 kilo ohm. Based on the graph, when R2 equals to 1 kilo ohm, the voltage detected is very small and almost near to 0 watt. Therefore, the oscillation frequency almost 0 Hz. When R2 is equal to 2 kilo ohm, the situation is still the same. The voltage detected is very small and almost equal to 0 watt, therefore the oscillation frequency is also 0 Hz. However, the situation will be different if R2 is increased to 10 kilo ohm and decreased back to 2 kilo ohm. The output waveform is shown as figure above, and the voltage will keep dropping until 0 watt after the circuit is run for a period of time. When R2 is increased to 3 kilo ohm, by observing the graph above, we can see the amplitude of the waveform is bigger than the previous one. So now, I will pass my time to Oyifong for the further discussion.
Based on theory, oscillation is not able to sustain when the gain A is less than 3. This is proven by the simulation of the circuit when R2 is equal to 1 kΩ in figure 2. From the calculation, it only provides a gain of 2. Next, based on theory, when the gain A is equal to 3, oscillation should be able to sustain. By observing figure 3 when R2 is increased to 2 kΩ, there is no voltage can be detectable. This may be due to the reason that the gain A must be greater than 3 to start an oscillation. Therefore, by increasing the value of R2 to 10 kΩ and then decreasing back to 2 kΩ, the oscillation should be able to sustain. However, after the circuit continuously runs for a long period of time, the voltage will eventually drop to 0 volts. If the voltage gain is too small, the oscillation will decay and eventually stop. Amplitude stabilization in the form of feedback diodes can make sure the oscillations continue indefinitely. This phenomenon may also be caused by the errors of the simulation software. In fact, there is a possibility for this condition to happen in real life due to the inaccuracy of resistors used in breadboards. Few errors did occur during the simulation. For instance, under the same circuit and conditions, the oscillation sustains when the gain A is less than 3, while the oscillation is not sustained when the gain A is more than 3. There exists also a difference in the value of maximum saturation voltage between the theory and the simulation. Theoretically or ideally, the maximum saturation voltage VCC should be equal to positive or negative 15 volts. However, in the simulation, the maximum saturation voltage obtained is lower than the VCC. Practically, this difference may be due to the positive saturation limit of the operational amplifier used or the tolerance that exists in the resistors. The difference between the ideal and practical voltage transfer is shown in the voltage transfer curve on the right side of the slide.
From this task 1, what I can conclude is the oscillation is not able to start when the gain A is less than 3. So, in order to start the oscillation, the value of A must be greater than 3. However, this oscillation still not sustained. So, to start the oscillation and to get the sustainable oscillation, the value of R2 must be achieved at the minimum condition, which is A must be equal to 3. Unfortunately, the result that we will get in this simulation may be slightly different compared to the real-life result due to the errors occurring during experiment, such as inaccuracy of resistor and the breadboard.
So the next task will be the stable multi-vibrator. A stable multi-vibrator is also known as free-running circuit. It is a switching circuit that produces non-stable output, which means the output will change from one state to another state all the time. It produces two constant square wave output waveform, and it can function continuously without any external triggering. Therefore, it is commonly used as the circuit design is simple and it is inexpensive.
This is the evidence of a stable vibrator simulation, where our group using the Multizen software for this simulation. There are a 4017 IC and 7 LED. We also have the 220 resistor, and there are 9-volt DC power supply, and also have 555 timer, potentiometer, 100 kilo ohm resistor, and finally we have a 1 microfarad capacitor. And to get the waveform, we are using the oscilloscope, which is the positive pin of oscilloscope we connect to the output of 555 timer, and the negative we connect to the ground.
Hi, I'm Mashila. I will present about result and discussion for a stable multivibrator. For the result, as you can see in the table, when RF is 0 mega ohm, the TH is 0.0693 second and TL is 0 second, where the frequency is 14.4 Hz and the duty cycle is 100%. When RF is 0.25 mega ohm, the TH is 0.24255 second and TL is 0.17325 seconds, while the frequency is 2.41 Hz and the duty cycle is 58.33%. When RF is 0.5 megaohm, the TH is 0.4158 second and TL is 0.3465 second, while the frequency is 1.31 Hz and the duty cycle is 54.55%. When RF is 0.75 megaohm, the TH is 0.58905 second and TL is 0.51975 second, while the frequency is 0.9 Hz and the duty cycle is 53.13%. And lastly, when RF is 1 megaohm, TH is 0.7623 second and TL is 0.693 second, while the frequency is 0.69 Hz and the duty cycle is 52.38%.
This is a waveform graph result when we use a different value of RF. Yeah, we can see here when we use a 0 mega ohm, the cycle is very small and there is no gap between the cycle. And when we use a 0.25 mega ohm, the gap is still small but larger than 0 mega ohm, and there is a small gap between the cycle. For 0.5 mega, you can see that the size of cycle bigger and the gap between the cycle also bigger. And we can see here for 0.5 mega ohm, the size of cycle is bigger than 0.5 mega and the gap between the cycle is also bigger than 0.5 mega ohm. And finally, we have the 1 mega ohm. We can see that the size of cycle is biggest than other and the gap also biggest than the other. So what we can see from the result is when the value of RF is increased, the size of cycle is bigger and the gap between the cycle also big.
For discussion, at potentiometer is 0 mega ohm, which at the minimum value, TH is calculated using equation 0.693 multiplied by C, open bracket, R1 plus RF, close bracket, where C is 1 microF, R1 is 100 kilo ohm, and RF is 0 mega ohm. Obtained pulse width is 0.0693 seconds. For TL is 0 second by calculating using equation 0.693 multiplied by C multiplied by RF. The duty cycle is obtained as 100% and the frequency is 14.4 Hz. The waveform graph shows that the line continuously simulate without having a gap between them. This is because TL is 0 second, so the LED will always be on. When the value of potentiometer is set to 0.25 megaohm, the LED blinks frequently that cause the pulse width TH is increasing to 0.24255 seconds, while the TL is 0.17325 seconds. But the duty cycle and frequency are dropped to 58.33% and 2.41 Hz respectively. From the wave graph form, the pulse width TH is longer compared to TL because TH value is higher than TL value as usual. By increasing the value until 1 mega ohm, the 7 LEDs are blink and bright time longer than before. At this time, the TH and TL will keep increasing based on calculation as the value of potentiometer is increased. The waveform will get more between TH and TL as both values keep increasing. From the calculation that can be observed, the duty cycle percentage is always more than 50%. Thus, by adjusting the value of potentiometer, RF will cause the value of TH and TL increase, the duty cycle decrease, the frequency decrease, and produce the square waveform.
So, from this assignment, we learn how an stable multivibrator function works. where we can calculate the TH and TL. We can find the oscillation frequency and the duty cycle after gain the TH and TL. From the observation, we notice that the duty cycle will be less than 50%. This is due to the pulse width. TH is always higher than the TL. Even so, we can adjust the duty cycle percentage to be less than 50% by adding a diode parallel to the resistor RF. Then it will shorten the RF resistor.